guys, Marco here from Aviator Live CS. Welcome back to the channel. Today we are going to continue reviewing the engines and APU system on the Boeing 737-800NG, and this is part 3 of this system. Today we'll be talking about engine system description. Let's review again an introduction about the engines we have in the 737-800NG. And what we have is two CFM56-7 engines. The engine is a dual rotor axial flow turbofan. The N1 rotor consists of a fan, a low pressure compressor, and a low pressure turbine. The N2 rotor consists of a high pressure compressor and a high pressure turbine. The N1 and N2 rotors are mechanically independent. The N2 rotor drives the engine gearboxes. A breather-powered starter motor is connected to the N2 rotor. A dual-channel electronic engine control, EEC, regulates each engine. The EEC monitors auto throttle and flight crew inputs to automatically set engine thrust. Each engine has individual flight deck controls. Thrust is set by positioning the thrust levers. The thrust levers are positioned automatically by the auto throttle system or manually by the flight crew. The forward thrust levers control forward thrust from idle to maximum. The reverse thrust levers control thrust from reverse idle to maximum reverse. Now, if we review the engine fuel system, the fuel is delivered under pressure from fuel pumps located in the fuel tanks. The fuel flows through a fuel spar shut-off valve located at the engine mounting wing stations. The fuel passes through the first stage engine fuel pump where pressure is increased. It then passes through the two fuel oil heat exchangers where IDG oil and main engine oil heat the fuel. A fuel filter then removes contaminants. Fuel automatically bypasses the filter if the filter becomes saturated. Before the fuel bypass occurs, the fuel filter bypass alert illuminates on the fuel control panel. So you can see them here. The second stage engine fuel pump adds more pressure before the fuel reaches the hydromechanical unit, or HMU, which is right there. To meet thrust requirements, the EEC meters fuel through the HMU. The spar fuel shut-off valve and engine fuel shut-off valve allow fuel flow to the engine when both valves are open. The valves are open when the engine fire switch is in. Remember, those switches are in, and the start lever is in idle position. Both valves close when either the start lever is in cutoff or the engine fire switch is out. A spar valve closed and engine valve closed lights located on the overhead panel indicate valve position. Fuel flow is measured after passing through the engine fuel shut-off valve and is displayed on the display unit. Fuel flow information is also provided to the FMC. All right, so we already talked about the normal display format and we talked about the primary and secondary indications in our previous videos. So please, if you didn't watch those yet, just click in the link above and you can go there and check it out. There are a couple of things, a couple of paragraphs actually, that I would like to read here, and I highlighted them. The EEC must receive electrical power to supply engine operating data to the flight deck engine indications. When the EEC is not powered, N1, N2, oil quantity, and engine vibration are displayed directly from the engine sensors. Positioning the engine start valve to ground supplies electrical power to the EEC and displays pointers digits for all engine parameters. During a battery start, with no power on the airplane, only N1, N2, and oil quantity are available. And I believe this is important to know. We don't do about battery starts very often, but now we know what happens if we have to do one and what we are going to see. The EEC is not powered until the engine accelerates to a speed greater than 15% N2. At 15% N2, the EEC becomes energized and pointers digits for all engine parameters are displayed. Now let's talk a little bit about the electronic engine control, or EEC. Each engine has a full authority digital EEC. Each EEC has two independent control channels with automatic channel transfer if the operating channel fails. With each engine start or start attempt, the EEC alternates between control channels. The EEC uses thrust lever inputs to automatically control forward and reverse thrust. N1 is used by the EEC to set thrust in two control modes, normal and alternate. Manual selection of the control mode can be made with the EEC switches on the engine control panel, which you can see here. Okay, the EEC normal mode uses sensed flight conditions and bleed air demands to calculate N1 thrust ratings. EEC compares commanded N1 to actual N1 and adjusts the fuel flow to achieve the commanded N1. The maximum rated thrust is available at the forward stop. The EEC limits the maximum thrust according to the airplane model. So here is where you can see, again, the switches in the aft overhead panel. Now, if we talk about the alternate mode on the EEC, we have two of them. We have the soft alternate mode and we have the hard alternate mode. Let's start with the soft mode. If required signals are not available to operate in the normal mode, the EEC automatically changes to the soft alternate mode. Alternate switch illuminates and the on indication remains visible. So this is what we are going to see, something like this. Okay. EEC uses the last valid flight conditions to define engine parameters, which allows the mode change to occur with no immediate change in engine thrust. This mode remains until the hard alternate mode is entered by either retiring the thrust lever to idle or manually selecting alternate with the EEC switch in the aft overhead panel. So now if we talk about the hard alternate mode, when selected, the EEC reverts to the alternate mode thrust schedule. Hard alternate mode thrust is always equal to or greater than normal mode thrust for the same lever position. If the mode is entered by reducing the thrust lever to idle while in the soft alternate mode, the alternate switch remains illuminated and the on indication remains visible. So we are going to see something like this again. Now, when alternate is selected manually, the on indication is blank. So we won't see this indication here. Thrust protection is not provided in this mode, and maximum rated thrust is reached at thrust lever position less than forward. Now, this small note here says if the EECs are in alternate mode, advancing the thrust levers full forward provides some overboost and should be considered only during emergency situations when all other available actions had been taken and terrain contact is imminent. The engine oil system. Oil from individual engine tank is circulated under pressure through the engine to lubricate the engine bearings and accessory gearbox. The oil quantity indicator, oil temperature indicator, oil pressure indicator, and low oil pressure alert are all located on the display unit. The oil system is pressurized by the engine-driven oil pump. Oil from the pump goes to the engine bearings and gearbox. Sensors for the oil temperature indicator, oil pressure indicator, and low oil pressure are located downstream of the oil pump prior to engine lubrication. Oil is returned to the oil tank by engine-driven scavenge pumps. From the scavenge pumps, oil passes through a scavenge filter. If the filter becomes saturated with contaminants, oil automatically bypasses the filter. Prior to the oil passing the scavenge filter, the oil filter bypass alert illuminates on the upper display unit. Prior to returning to the oil tank, the oil passes through the main engine oil cooler where it is cooled by engine fuel to maintain proper oil temperature. Engine start system. Start operation requires pressurized air and electrical power. Air from the bleed air system powers the starter motor. The APU, an external ground card, or the other operating engine provides the bleed air source. In the ground position, the engine start switch uses battery power to close the engine bleed air valve and open the start valve to allow pressure to rotate the starter. When the start valves open, an amber start valve open alert is provided on the upper display unit. The starter rotates the N2 compressor through the accessory drive gear system. When the engine accelerates to the recommended value, 25% N2 or max motoring, moving the engine start lever to the idle position opens the fuel valves on the winch part and engine and causes the EEC to supply fuel and ignition to the combustor where the fuel ignites. Initial fuel flow indications lag actual fuel flow by approximately 2 seconds. Therefore, during engine start, an EGT rise may occur before fuel flow indication. At a static cutout speed, approximately 56% N2, power is removed from the start switch holding solenoid. The engine start switch returns to off. The engine bleed air valve returns to the selected position, and the start valve closes. So that's basically the engine start process for the Boeing 737-800NG. Okay, to complete today's video, we'll be talking about some of the protections we have, and we'll start with the structural limit protection. The EEC provides N1 and N2 red line overspeed protection in both normal and alternate modes. The EGT limit must be observed by the crew because the EEC does not provide EGT red line exceedance protection. Idle operation. The EEC automatically selects ground minimum idle, flight minimum idle, and approach idle. Ground minimum idle is selected for ground operations, and flight minimum idle is selected for most phases of flight. Approach idle is selected in flight if flaps are in landing configuration or engine anti-ice is on for either engine. At the same airspeed and altitude, N1 and N2 RPM will be higher for approach idle than for flight minimum idle. This higher RPM improves engine acceleration time in the event of a go-around. Approach idle is maintained until after touchdown, when ground minimum idle is selected. In flight, if a fault prevents the EEC from receiving flap or anti-ice signals, approach idle schedule begins below 19,000 feet MSL. During ground starts, the EEC monitors engine parameters to detect impending hot starts, engine stalls, EGT start limit exceedances, and wet starts. These protection features do not function during in-flight starts. If an impending hot start is detected by a rapid rise in EGT or EGT approaching the start limit, or a compressor stall occurs, the white box surrounding the EGT digital readout flashes white. The flashing white box resets when the start lever is moved to cutoff, or the engine reaches idle N2. Current versions of EEC software 7BQ and later automatically turn off the ignition and shuts off fuel to the engine for an impending hot start or stall. If the EGT exceeds the starting limit, the EGT display, both box and dial, turn red. The EEC automatically turns off the ignition and shuts off fuel to the engine. The alert terminates and the display returns to white when EGT drops below the start limit. Following shutdown for both engines, the EGT box turns red to remind the crew of the exceedance. A wet start occurs if the EGT does not rise after the start lever is moved to idle. If a wet start is detected, the EEC turns off the ignition and shuts off fuel to the engine 15 seconds after the start lever is moved to idle. Okay, so guys, this is the end of the video for today. I hope you liked it. If you did, please give me a thumbs up. If you are not subscribed to the channel yet, please do it now. And if you think these videos could be useful for somebody else, please share them. And that's going to help me a lot to grow the channel. Hopefully next week we'll continue with the engines and APU. Until then, guys, take care and hope to see you soon.